Our next speaker is Jeff. He's currently a researcher at Meta, and he's working on video generation. Before this, when he was doing his PhD, he published StreamV2V, which is a temporal consistency layer on top of stream diffusion. This will help increase the video quality and the smoothness of the output. And I really like his work because I think it perfectly represents this idea of open source collaboration and innovation as a community, right? Jeff created StreamV2V that helps improve upon Chenfeng's work for stream diffusion. So here, I want to introduce Jeff. Take it away.
Thank you, Eric. Yeah. So my name is Jeff. I'm really excited to share my work, StreamV2V, which is a 1-year-old work. So, like 1 year in AI is like 1 decade in other eras. So I will try to, even though it's an old work, so I will try to tell the story behind this work and to share my experience how we develop this work. So this work is joint work with Chenfeng and other peers from UT Austin and UC Berkeley. So when we first talk about video-to-video translation, before GenAI, we usually talk about like traditional filters or visual effects. So you get an input video, and what you probably do is to go to some website and to find some filters, right? And here is grayscale filters. So for these traditional filters, they are really, really fast, and they can do that in real time. But you are now only limited number of filters, and they have very bad edit capability. And they can only change the histogram of the video, and they cannot do very creative works. Recently, we have diffusion models, and we have diffusion model-based video-to-video model. So we can change the panda to Chinese ink painting, or we change the panda to koala. And for the lady, we can change to other styles, and we can swap the lady to Greek statue. But for these prior diffusion models, they are really, really impressive. They are really powerful. But they can only, like previous speakers have all mentioned this, they can deal with very limited length of videos, like 4 seconds, and they're extremely slow. Just like 1 year ago, it will take like 1 minute to get 4-second output. How can we get like the best of both worlds? So before I jump into the solution, let me elaborate a little bit why existing diffusion models are slow. So actually, Chenfeng already talked about this because the existing video diffusion models, they are treated video as a chunk. So they are treated as a batch, and then you put this batch into a diffusion model, and the output will also be a batch. Because all the frames are loaded into the GPU, and the memory will increase with number of frames that you process. So when you reach a limit, so you can deal with that amount of frames. So what we want to do is share the same spirit of stream diffusion theory, is to do it in a streaming fashion. So when we have real-time video, when every frame comes, we just process it and output that frame and on the fly, so that we can deal with it in real time. If you look at the memory consumption chart on the right, for batch processing, it will increase, the memory cost will increase with the number of frames. But for the streaming process, we maintain a constant memory, which means that we can get unlimited length of videos. Okay, this is a highlight of demo of my work, StreamV2V. This is on one RTS 4090. Again, so this work was done like 1 year ago. So if you look at the quality, it's not that good. But the idea is that we can change. Okay, let's change to my boss, Mark Zuckerberg. Okay, and we can also change to Leonardo DiCaprio. If you look at the background, it transfers the boxes into your house, which means the model understands the Leonardo DiCaprio And we can also do some stylization. So this is a pixel art style. And this is 3D poly style, I'm assuming. So we can also do like claymation style. But the consistency is not that good, I would say, if we take in the standard of nowadays. Okay. So how are we able to achieve this stream diffusion? So our starting point was the stream diffusion. Chen Feng already talked about this. So the base idea of stream diffusion is that we batch the different level of noise latent into a batch so that we can compute them in a batch manner to utilize the parallelism of GPUs. But for within the denoising batch, however, all the latent, they are calculated independently, which means stream diffusion is still an image-to-image model. So this figure is more obvious. So if we look at, so we have the first frame I1, and we process it, get the output. For the second frame I2, we process it, get output. But there is no correlation. There is no low dependency of all the frames. So this is the first version of stream diffusion demo. If you look at background, is flickering. But nowadays, stream diffusion V2 is much better. You definitely need to try that. So how are we able to improve over the stream diffusion? So this idea has also been mentioned a lot of times by David, like the context, the memory, and Dr. Xun on the causal, utilize the memory. So for this approach, I'm actually using the same spirit. It's like looking backward to using the memory. So the basic idea is, okay, when we generate the first frame, I1, we get the output. When we are generating the second frame, the I2, we want the model to look at how we generate the first frame. Thinking that you look backward how we generate the first frame, then you can draw some link when we generate the first frame to get a better consistency. So for the third frame, we look at how we generate the first and second frame, and then get a better, more consistent third frame with the first and second frame. That's the key idea. So the next question is, how are we able to implement this kind of memory mechanism into the diffusion model, especially if our base model is an image diffusion model? How are we able to incorporate this memory mechanism? There are several alternative solutions, like you train a video diffusion model, or you include other methods you train with video. But for this one, my base model is a diffusion model, and I didn't include any training. So it's a training-free method. Okay, so the basic major idea is I utilize the diffusion models, the diffusion features within the diffusion model. So for diffusion model, you have several layers, right? You have features, you have activations in several layers. Let's say we get one layer, and we can cache or we can store the intermediate diffusion features. And we get, for attention, we get query, key, and value. So we K1 and V1, they are keys and values of the first frame, and so for the following frames. Okay, so now we want to pick a point on the fifth frame, so the latest frame. So the dot P is on the person's goggle. So this is a red point. So what we want to do is to calculate the activation or the attention or the relation, whatever you want to call it. We want to get the correlation of this point with the attention maps of the previous frames. And we can get a heat map here. So if the color is red, which means that we have higher response. If we get the point with maximum activation is, they are all lie on the point on the goggle. So which means that the cached self-attention features contain like very rich information of the previous frames, which we can average to generate a better, more consistent output. So our solution is to get a feature bank to improve the consistency. Thinking that we have the current frame, we get a feature bank, and we fetch the information of the previous frames. And here we get two like modules to utilize this to utilize the store features. One is called EA, is called extended server attention. The idea is very simple. So this is a standard attention, right? We get an input XT and we get a QKV, and we do attention operation. Here we have a feature bank, which stores the information of the past frames, and then we can fetch, we can get that the keys and the values of the past frames, and we can cut them together with the current frame, and we do the scaled out production. Okay, so this is a extended server attention. The other way is more straightforward. We do directly feature fusion of each transformer block. So the idea is, okay, we get this output of this block, and we also have a feature bank store the features of this exact same place. And then when we get the feature, we match it with similarity. So thinking that from our previous example, we are fusing the feature of the goggle of the first frame to the fourth frame to the current fifth frame, and to get a more smoother and more consistent output. And after we have done this extended server attention and feature fusion, we can update and save the memory bank. So I will talk about this part later. Yeah. Okay, so by doing this, we can leverage the past information and get a more consistent output. How are we able to, so the current problem is how are we to get this bank, right? So an ideal case is that we have infinite memory that we can store all the information of the past frame. But the caveat is if we store all the features of the past frames, then our memory of the feature bank will increase, right? It still will be out of memory. So there are two solutions. One is a naive queue. We get a queue here. So the bank size is 2. And for the T1 is the feature map of the current frame. And we append the feature into the bank. And when we have the second frame feature, we append it to the bank. But when we have the third frame coming in, remember that the size of the bank is 2, so we get to pop out the past frames. So we get to pop out the first frame. And also for the fourth frame, we have to pop out the second frame. So this is problematic, right? So the first problematic is it has limited span because you always have to pop out the features of the past of the very far frames. And the other problem is there are many redundant features. You are only storing the nearest closed features, which are if there's not quite a motion, so the features are redundant. So our solution is utilize a technique called dynamic merging. So the basic idea is, okay, when we have the first frame coming in, we append the features into the bank. When we have the second frame coming in, we do a merging. So the basic idea is we only keep the unique information as much as possible while keeping a very compact size. So for the T1 and T2, we merge them together, we get this T12. For so on and so forth for the third and fourth frame. So we always keep a very compact size of memory bank, so which is size 1. And theoretically, but practically not, theoretically we get unlimited span because we didn't like forcefully pop out the previous features. Rather, we merge the previous features in the current time step. So for a bit more detail about the dynamic merging, so for when we get these two feature maps, we just concatenate them together and randomly divide it into two sets, set A and set B. And then for every set in set A, in set B, we find, instead A actually, instead A, we find the most similar feature in set B, and we merge them together. We do a weighted average. So this is not a novel idea in the transformer or diffusion space because we have token merging. But for my work, it's done from the temporal dimension. Yeah. Okay, there are some evaluation results. Because there are 4 papers. And this is the quantitative comparison. This is a really hard comparison, I would say. We also did a user study. So basically, our stream diffusion is better. Our StreamV2V is better than stream diffusion and code depth, and it's comparable with re-render. Those are Asian names. You probably don't know, but they're quite famous 1 year ago. But it's worse than flow weight and token flow. But our model is really fast. It's 100 times faster than the state of art at that time, token flow. Also, the feature bank idea, even though it's designed for video to video, it provides some bonus for continuous text to image. For continuous text to image is that you continuous type, and then you will generate or give you the output instantly. So if without the feature bank is a pure image model, it has no dependent on the previous frames, right? So you cannot expect what you will get when you type the next character. But with this feature bank, look at the right, we actually get much smoother transition between the frames. We do have a lot of limitations. First limitation is our model is based on image diffusion model. If the image diffusion model cannot do the edit, our model will fall as well. So the stable diffusion 1.5 cannot change myself to Batman, so the model will fail. The other is, again, this because StreamV2V is an image diffusion model, it cannot deal with very quadratic motion of the camera and the subject. Yeah, that's all. Thank you.